So the first part is not that difficult. Let's start with point A. We know that point A lies on top of the x-axis, which means that the y value is 0. With that in mind, we can sub in 0 onto this equation to get that cosine of x is also 0, which means that x in this the first time that cos x crosses 0 has to be when x is pi on 2, I think. Yes, cosine, because cosine curve runs like this, and this is pi, this is half pi, this is 3/2 pi, and this is 2 pi. So with that, we know that for point A, we have the coordinate pi on 2, 0. Next up, we have point C, where x coordinate we know is 0, so x equals to 0. Then to find y, we just sub in everything as 0. So cosine of 0 is plus 1, on top of 2 take sine 0 is 0, which gives us just a half. And therefore C have the coordinate 0, half. So that's the 2 points that we're looking for. So we now need to find dy by dx. To do that, we just need to differentiate by dx. The most convenient way that I can see is to just go for the quotient rule, which gives us dy by dx equals to u times the actually that's phi du by dx, which gives me minus sine x. Take away u d phi, and that would give me minus cosine, or divide by phi squared. And with that, you expand this to get minus 2 sine x plus sine squared x plus cos squared x. And we can combine this into 1. So 1 take 2 sine x on 2 take sine x squared is the dy by dx. Now we need to find the exact coordinate of b, where b is the turning point, which means that dy by dx is 0. And so 0, in order to get a stationary point, 1 take 2 sine x must be equal to 0, which means that sine x is a half, and so x is pi on 6, or 30 degrees. And for the purpose of this question, I just went with radians. Now we need to find the y value of b. And to do that, we just sub in pi on 6 onto this whole expression, which means that cosine of pi on 6 divide by 2 take sine of pi by 6. Sine of pi by 6 is just a half, as well shown. So we get 3/2 at the bottom. Cosine of pi by 6 is root 3 on 2, and then we can get just root 3 on 3, or if you fancy 1 on root 3, either way works. I personally prefer to rationalize my answers. So yeah, but I think they wouldn't penalize you for writing 1 on root 3 either. So yeah, that's question part 8 part 2 done. Part 3a, we need to use integration to find the area enclosed by the curve. And we already know that x coordinate of a is pi by 2, so that would be our upper bound. The lower bound will be just 0 because that's the y-axis. Then we want to put y dx or cos x on 2 take sine x dx. So normally for these kind of fractions, you'd substitute the bottom by a variable, then kind of try to cancel things out, and this is no exception. So let's take u equals to 2 take sine x, and so we have du by dx equals to minus cos x, and by just substituting we get sine of pi by 2 is 3 halves, or sine of pi by 2 is a half. Wait, actually no, it's 1, so that's 1 rather, and sine of 0 is 0, so we've got 2, so actually it's 1 and 2. Then we have cosine of x on u. We want du, and so we also have a minus cosine x on the bottom, and they in fact cancel, which means that this is the correct substitution. And so we have 1 on u, negative from 2 to 1 du, and that would give us natural log of u between 2 and 1, which should give us naturally just natural log of 2. So because natural log of 1 is just 0, so it's natural log 2 take 0. So that's part A done. Part B is a little bit more tricky. There are 2 ways of doing this, and one way is to directly use the value given. The other one is to actually derive the k expression. For the purpose of this video, I'm gonna prove this expression. Feel free to just sub in, and it would work either way. So in order to get half the area, we need to state that the area after integration will be half ln 2, because the total area is natural log of 2, is equal to integrate from k to 0 to k, or from k to pi on 2. Yeah. Then we put in the exact same expression dx, use the exact same substitution. We should be able to get let's see, minus natural log of 2 take sine x from k to 0. So I just skipped like 5 steps in a row because we've done that in previous steps. But in fact I just swapped u into the x term because we can't actually do anything with the k. So after changing the variable to u, I changed it back to x again. So this is just minus natural log u. With that, we substitute in the k values to get minus natural log of 2 take k minus the minus log of 2 take 0 gives me half ln 2, and negative negative goes to the positive, and so rearrange to get natural log of 2 take k is half ln 2. And we can rearrange this. Actually this is not k, this is sine k, and this is 2 take sine 0, which is 0. Same here is take sine k. Let's see. Then if we take a half power, so use the log rule, exponents this prefix to natural log of 2 to the half is equal to natural log of 2 take sine k. Because the natural log are on both sides, we can take exponents on both sides, and states that sine k is actually just 2 to the half is root 2. Let's see, I did rearrange the root 2 over to the left and the sine to the right, but I just flipped the other side. It still works. And so k is just arc sine of 2 take root 2, which is not surprisingly the same as the given value. So yeah, that's it for question 8. Finally, question 9, part 1, show the f(x) is odd and interpret this result in terms of a graph. So let's see. The definition of an odd function is f(x) is equal, actually the better definition is f of minus x is equal to negative f(x). This is the definition of an odd function, and so we can show that f of minus x in this context would be minus x cubed e to the minus x squared. Minus x cubed gives us a negative x cubed, e to the minus x squared gives us just x squared, which is conveniently negative f of x. And so we have proven that it is an odd function. On top of that, all odd functions will be able to have a rotational symmetry, 180 degree from the origin. Say a typical x cubed graph will look something like this. This is probably like more x cubed minus 3x or something, but that's the general idea. You can take a rotational symmetry 180 degree and you'll get the same curve. So write that down as rotational symmetry 180 degree at 0, 0. That would give you all the marks you need for part 1. For part 2, find the coordinates of the stationary points of the curve. So stationary points means that we want to differentiate. So dy by dx is, by product rule, 3x squared e to the minus x squared plus x cubed e to the minus x squared times minus 2x. and that equals to 0. And so rearrange to, actually don't rearrange because that would lose your information. So 3x squared e to the minus x squared take 2x4 e to the minus x squared. We can factorize out x squared e to the x squared to get 3 take 2x squared times the x squared e to the x squared equals 0. So either x is 0, e to the x squared is 0, which cannot happen, exponents don't have 0 value, don't range, and or 3 take 2x squared is 0. So that would imply that 3 is 2x squared and 3 on 2 is x squared, and so x has to be plus or minus square root of 3 on 2, and plug that into the calculator to give answers to 2dp. It's not really necessary, but you can do that if you want, or for the purpose of this question, do so. Yeah, that's the first bit. Then we need the y coordinates. And to get the y coordinates, we sub in the values into the equation. So y is either 0 at 0, 0. So we've got point 0, 0 as the first stationary point. Or we can have, if we have a root 3 on 2, then y will be equal to root 3 on 2 cubed e to the minus x squared, which is just 3 on 2. And yeah, basically plug this into the calculator and it should give you some value y1, let's say. And for the second point, you just do the same except it's negative because it's odd. And plug this into the calculator as well. You should get minus root 3 on 2 y2. And so that's all the stationary points for question 9, part 2. Part 3, sketch the curve for minus 2 to 2. That would be interesting to sketch. So first of all, we do have a stationary point at 0, 0, so that should be set and done with. We also know the two other stationary points, one on the positive domain, one on the negative domain. We know that it is a, we do not really know if it's stationary point as of a maximum or minima or inflection, so we can do that by differentiating. So let's give this a try. To differentiate the expression f dash x, that's the original thing that we have derived. This is dy by dx, by the way. This dash is another way of writing down differentials. So if we differentiate twice, f dash dash x, we again apply the chain rule. 6x e to the minus x squared plus 3x squared e to the minus x squared times minus 2x take 8x cubed e to the minus x squared, take 2x to the 4 e to the minus x squared times 2 minus 2x. That would give me 6x e to the minus x squared, take 6x cubed e to the minus x squared, take 8x cubed e minus x squared plus 4x 5 e to the minus x squared, and we can just substitute in the x value on calculators, use the answer function for this, I guess, and we should be able to get that for x equals to plus root 3 on 2, f dash dash x is greater, actually it's less than 0, which means that it's a max, and for x is minus root 3 on 2, f dash dash x is larger than 0, give us a min, and for x is 0, it's conveniently just 0, which gives us inflection, which means that in order to fit the curve, we have a maximum and inflection that goes up, then goes down, forced to be a minimum, and it terminates before it reaches the x-axis, because it only goes up to x is x is minus 2 and x is 2. So yeah, this is the general shape. Make sure you do it like smooth, not like my sketch, because it's kind of bad. But anyway, this is the general shape, and you can see the rotational symmetry from part 1, which should be what you're looking for. So for part A, use the substitution t equals x squared to find this integral, where and also determine k. So let's give this a try. Integrate x cubed e to the minus x squared dx, where t is x squared, gives us t x e to the minus t dx, and in order to get anywhere in bounds of dt, we need to first find dt. 1 dx is 2x, which means that dx is just dt on 2x, so we get t x e to minus t dt on 2x. The x cancels, which is nice to see, and we get half of t e to minus t dt. And so we can say just by inspection k equals to a half. So that's A done. Then B, find the exact area where x is it's where the between the x value 2 and 0. That's what I mean to say. So let's get this started. So let's start with the integral of half t e to the minus t dt, and we know that t is x squared, which means the boundary is between t 2 squared and 0 squared, which means that it's from 0 to 4. With that, we integrate using by parts. So u equals to t, u dash equals to 1, dash is just a shorthand form of differentials. Phi dash is e to the minus t, and phi has to be minus e to the minus t. Then this whole expression will be, let's see, it will be u phi, which is minus t e to the minus t between 4 and 0, take integrate minus e to the minus t dt, which means that first let's try this is minus 4 e to the minus 4 just minus 4, then you take away 0 because 0 times 0, 0 times e to the 0 is still 0, then you add a negative e to the minus t in between 4 and 0, should give you 4e to the minus 4, take e to the minus 4 plus 1, because e to the 0 is 1 and minus 1 is plus 1. Then expand the expression to get half, take 5 halves e to the minus 4. And that should be the answer for 9.4b. And this will be the last answer for this paper. In conclusion, this paper, this Core 3 paper is not the easiest paper. It's definitely doable. Section B is relatively straightforward, I'd suggest. Maybe sketching the curve for question 9 might be a little bit more challenging if you didn't find the stationary point, like the types of stationary points. But normally it's alright. Section A is comparatively challenging, but it's, again, like I said last video, it's doable for sure. So with practice, definitely C3 is quite a nice paper to go on with. Anyway, this will be it. If you have any questions or suggestions, do leave me a comment below. And good luck tomorrow for the ones who are doing it tomorrow. And for the ones in the future, since the spec is gonna be changing soon, I expect to have to do a lot of the new spec this summer. So stay tuned for that, and I will see you again possibly in the future.